everyone, and welcome to Complicated Stuff on the Girl Has It All channel. I'm Thomas, and we are ready for episode 8 of our deep dive.
8.
Into all things complex and fascinating. As always, I am joined by the brilliant Jenna, our resident quantum expert and fellow Girl Has It All team member.
That's me.
We're going live every Friday and Saturday.
Yeah.
Make sure to tune in.
Yeah.
You can also catch the premiere on our YouTube channel at 6:30 p.m. But enough about all that stuff. Let's get right into it. Today's cosmic mystery. We're talking about the possibility that dark energy, the force supposedly driving the universe's accelerating expansion, might not actually exist.
Yeah. So to even understand why that's a question, we need to touch on the current prevailing model of the universe.
Okay.
Which is called the lambda CDM model.
Lambda CDM model.
It incorporates dark matter and dark energy to explain certain observations, but it's not without its problems.
What kind of problems are we talking about?
Well, one of the biggest challenges is the uneven distribution of matter in the universe. We see these massive clusters of galaxies, and then we see these vast empty voids.
Right.
This lumpiness doesn't quite fit with the smooth, uniform expansion that the standard model suggests.
I see. Okay, so then how does this new theory, Timescape Cosmology, address this lumpiness?
So Timescape Cosmology kind of flips the script. Instead of invoking dark energy, it suggests that different areas of the universe experience time differently due to these variations in gravity.
Yeah.
And remember, Einstein's theory of relativity, gravity affects the flow of time.
Okay.
The stronger the gravitational pull, the slower time passes.
So are you saying time isn't constant?
That's exactly
With the universe.
what this theory proposes.
Whoa.
So in areas packed with matter, like those big galaxy clusters, gravity is stronger.
Yeah.
So time runs a bit slower.
Okay.
Compared to those vast empty voids where gravity is weaker.
I see. So different pockets of the universe have different clock speeds.
Yeah.
How does this relate to the universe's expansion?
Because time flows faster in the voids, they've had more time to expand.
Okay.
Compared to the denser regions where time moves slower. So when we observe the universe, it looks like the expansion is accelerating, even if it's not.
Right.
It's just that some parts have expanded more because they've had more time to do so.
So the apparent acceleration is an illusion.
Exactly.
Caused by these varying rates of time flow.
Precisely. It's a pretty radical shift in perspective.
Okay.
No need for this mysterious dark energy pushing everything apart.
Yeah.
Just good old gravity. And the concept of time being relative, as Einstein predicted.
Right.
It's like watching two runners start a race at different times.
I see.
Even if they run at the same speed, the one that started earlier will naturally be farther ahead.
Yeah, that's a great analogy.
Yeah.
So it seems like this theory relies on things that we already know, like gravity and Einstein's theories.
Yeah.
But is there any observational evidence to support it?
Actually, yes. 2 recent studies analyzed data from over 1,500 Type Ia supernovae. These are incredibly bright stellar explosions that act as standard candles, meaning we know their intrinsic brightness.
And knowing their true brightness lets us
figure out how far away they are and how fast they're moving.
Okay.
Think of it like a light bulb. You know how bright a 100-watt bulb is? If it seems dimmer, it's farther away.
Right.
These supernovae work the same way, allowing us to gauge distances and speeds in the vastness of space.
So what did these studies reveal when they looked at supernovae through the lens of Timescape Cosmology?
The Timescape model actually fit the supernova data better than the standard model with dark energy.
Wow.
It's pretty compelling evidence suggesting this model might paint a more accurate picture of the universe than our current understanding.
So this is really shaking up our understanding of the cosmos.
Yeah.
If this model is accurate, does this mean the universe doesn't have a single age?
That's one of the most mind-blowing implications. If different parts of the universe are experiencing time differently, it wouldn't make sense to talk about a single universal age.
Wow.
Our corner of the cosmos might be 13.8 billion years old, but in those vast voids where time ticks faster, it could be significantly older.
This is truly incredible. We need to take a moment to process all of this, but when we come back, we'll delve even deeper into the implications of Timescape Cosmology. What does it mean for the future of the universe? What other mysteries could it solve? Don't go anywhere. We'll be right back.
See ya. Welcome back, everyone. It's amazing to think that our exploration of the universe could lead us to rethink something as fundamental as time.
Absolutely. Before the break, we were talking about how Timescape Cosmology challenges our notion of a single universal age.
Right.
But what does it mean for the future? What happens to this lumpy universe in the long run?
That's where things get even more interesting. The standard model with DarkEnergy predicts kind of a bleak future. The universe keeps expanding forever, becoming this cold, dark, and empty place.
A cosmic fate.
Yeah, it's called the Big Freeze.
Right, not a very cheerful ending.
Exactly. But Timescape Cosmology offers a different perspective. Remember, in this model, the apparent acceleration is an illusion caused by these varying rates of time flow.
Right.
So the universe might not be accelerating at all. It could even be slowing down.
Wait, so instead of eternally expanding,
Yeah.
the universe could actually start contracting at some point.
It's a possibility. If the expansion is indeed slowing down, gravity could eventually take over, pulling everything back together in a cosmic big crunch.
Oh, wow.
It's like throwing a ball up in the air. Eventually, it stops rising and falls back down due to gravity.
Wow, that's a much more dramatic scenario than the Big Freeze.
Yeah.
So we have a potential big crunch, or maybe the universe keeps expanding at a steady rate. What other possibilities does Timescape Cosmology suggest?
There's another fascinating scenario. Imagine the universe expanding for a while, then contracting due to gravity, then expanding again.
Oh, wow.
It's like a cosmic yo-yo oscillating between expansion and collapse over vast timescales.
So the universe's future could be a big crunch, a cosmic yo-yo act, or maybe even a steady, non-accelerating expansion. It seems like this new model really opens up the possibilities.
It definitely throws the doors wide open for different cosmic destinies. But remember, these are still theoretical possibilities. We need more data and further research to determine which scenario is most likely.
Of course. But beyond these grand scenarios, I was intrigued by something else mentioned in the articles you shared. It seems Timescape Cosmology might also have the potential to solve some of the biggest mysteries in physics.
You're talking about the cosmological constant problem.
Exactly. Can you explain this problem for our listeners who might not be familiar with it? What is this cosmological constant, and why is it such a big deal?
So think of the cosmological constant as a measure of the energy density of empty space.
Okay.
Even a perfect vacuum, completely devoid of any matter or radiation, still has some inherent energy. It's the baseline energy level of the universe.
So even nothingness has energy.
It is, and here's where the problem arises: quantum field theory. Our best theory for describing the subatomic world predicts that this vacuum energy should be enormous, unbelievably huge. But when we actually measure the cosmological constant from astronomical observations, it turns out to be incredibly tiny, like 120 orders of magnitude smaller than the theoretical prediction.
120 orders of magnitude. That's like saying the distance to the nearest star is actually the width of a human hair. It's a mind-boggling discrepancy.
Exactly. It's a massive mismatch that has puzzled physicists for decades. It's like finding a tiny pebble where you expected a mountain.
So how does Timescape Cosmology offer a potential solution to this problem?
Remember how we talked about different parts of the universe experiencing time differently?
Right.
Well, if the flow of time varies throughout the universe, it could affect how we measure the cosmological constant.
Are you saying our measurements of the cosmological constant might be skewed because we're observing it from a region of space-time where time flows differently from other regions?
That's the idea. If Timescape Cosmology is correct, it means the cosmological constant might not be constant at all. It could vary depending on the local flow of time.
That would certainly explain why our measurements are so drastically different from theoretical predictions. So by simply acknowledging the lumpiness of the universe and its effects on time, this model might solve one of the biggest mysteries in physics.
It's a fascinating possibility and a testament to the interconnectedness of physics and cosmology. Understanding one can profoundly impact our understanding of the other.
This is all so mind-blowing. It's incredible to think that something as fundamental as time could hold the key to unlocking some of the universe's deepest secrets. We'll need another break to absorb all of this. But stick with us, because when we come back, we'll explore what Timescape Cosmology means for our place in the universe and what questions this mind-bending model leaves us pondering. Welcome back to Complicated Stuff. It's amazing how exploring these cosmic concepts can really make you question everything you thought you knew about the universe.
It really is. Like, we often take for granted that time is this constant universal thing ticking away at the same rate everywhere. But Timescape Cosmology throws that notion right out the window.
Exactly. And while we were getting ready for this part, I kept thinking about this quote from physicist David Wiltshire that you shared.
Yeah.
He said that dark energy might just be a misinterpretation
Yeah.
of how the universe expands because we've been assuming it's smooth and uniform, when in reality it's anything but.
Wiltshire's work is really at the forefront of this field. He emphasizes how the lumpiness of the universe, those massive clusters of galaxies and vast empty voids, can significantly distort our perception of cosmic expansion.
Yeah, it's like trying to measure the speed of a river by only looking at a small section.
Right.
You might think it's flowing at a constant rate, but if you zoom out and see the whole river with its bends, wraps, and calm stretches, you realize it's much more complex.
That's a perfect analogy. Timescape Cosmology is about taking that zoomed-out view, considering the universe's structure and how those variations in matter density and gravity influence the flow of time.
Okay.
Ultimately, it's about acknowledging that our observations might be influenced by our local time zone, so to speak.
So it's not that dark energy doesn't exist at all, but maybe we've misidentified it
Yeah.
because we weren't factoring in the complexity of the universe's structure and the implications of Einstein's theory of gravity.
Precisely. It's a reminder that our understanding of the universe is constantly evolving. New data and theoretical frameworks can challenge our most cherished assumptions.
Which brings us to what I find to be the most profound implication of timescape cosmology.
Okay.
If different parts of the universe are experiencing time at different rates,
Yeah.
what does that mean for us? What does that mean for our place in this vast, ever-evolving cosmos?
That's a question that kind of delves into both physics and philosophy. It challenges us to rethink our perception of the universe, its history, and our place within it. If time is relative on a cosmic scale, then our view of the universe is inherently linked to our location in space-time.
It's almost as if we're each experiencing our own unique version of the universe, shaped by the specific gravitational field we inhabit.
That's a fascinating way to put it. It raises questions about the nature of reality itself. Is there an objective universal reality out there, or is it all relative to our individual experience of time and space?
Well, those are some pretty heavy questions.
Cosmology has a way of doing that. It pushes us to contemplate these fundamental mysteries about existence, consciousness, and the nature of reality.
I think that's what I find so captivating about this whole discussion.
Yeah.
Timescape cosmology isn't just about revising our understanding of the universe's expansion. It's about expanding our minds. It's about pushing the boundaries of our knowledge and embracing the mystery and wonder of the cosmos.
I couldn't agree more. The universe is full of surprises, and there's always more to learn and discover.
Well, Jen, it's been an incredible journey exploring these mind-bending ideas with you today. Thanks for joining me.
Well, the pleasure was all mine, Thomas. It's always exciting to dive into these complex topics with you.
And to our amazing listeners, thank you for joining us for episode 8 of Complicated Stuff on the Girl Has It All channel. We go live every Friday and Saturday, so make sure to tune in and don't forget to catch the premiere on our YouTube channel at 6:30 p.m. We love connecting with you all, so feel free to reach out on social media and let us know what you think of the show. Until next time, keep those minds curious and never stop exploring the universe.
You see y'all next week. Bye.